Welcome to The Explainer. Today we're getting into something pretty incredible, how our muscles actually work. We're going to uncover the science that takes a simple thought and turns it into pure physical force.
I mean, really think about it for a second. How does a simple idea, just an intention in your head, become the raw power you need to lift a heavy weight or sprint across a field? It's this amazing connection between our mind and our body. Well, it turns out it's a fascinating journey. We're going to travel from the tiniest electrical sparks in your nervous system all the way down to these amazing little molecular machines that are chugging away inside every single one of your muscle cells. All right, so it all starts at this really specialized connection point. This is where your nervous system basically gives your muscles their marching orders. It's called the neuromuscular synapse, and you can just think of this as the electrical switch that turns on the whole muscle engine. It's that crucial handoff from nerve impulse to actual physical movement. Okay, so the switch has been flipped. Now, let's zoom way in, deep inside the muscle fiber, to see the incredible machinery that actually creates all that force. And here it is. This little structure is called the sarcomere. And this, right here, is where all the magic happens. It's the basic engine, and it's repeated millions of times over in just one muscle. So, the engine has a few key parts. First up, you've got these thin filaments called actin. The best way to think of them is like a really sturdy rope, or maybe like tracks that the movement is going to happen on. And if actin is the rope, then myosin is the team that pulls it. These are the thick filaments, and they have these little heads that are the actual molecular motors. They are literally a molecular tug-of-war team. So here's how this brilliant little cycle works, and it happens in the blink of an eye. First, that signal arrives from the nerve, and that causes calcium to flood the area. The calcium basically unblocks the actin rope, giving the myosin team a place to grab on. Then they bind. The tug-of-war team grabs the rope, and then comes the power stroke. They use a little bit of energy to pull that actin rope, which shortens the entire muscle. And finally, a new bit of energy comes in, tells the myosin head to let go, reset, and get ready to pull all over again. It's this constant cycle of grabbing, pulling, and resetting that creates all movement. Now, that whole sliding filament theory is it's elegant, right? It's what you learn in every textbook. But here's the really cool part. Science is showing us that it might not be the whole story. And that's what's so fascinating. This quote really drives it home. Even with something as fundamental as muscle contraction, a process we think we know so well, there are still these huge unanswered questions. I mean, we still don't know the exact force that makes those little myosin heads pivot. We're not totally sure why the muscle thickens when it contracts, or even how it fully relaxes and gets back to its starting state. It's just a great reminder that science is an ongoing process of discovery, not just a book of facts. So let's zoom back out. Let's go from a single, microscopic pull to the long-term story of how our muscles get stronger and bigger. This process is called hypertrophy. And to understand it, you have to know about myonuclei. Now, most cells in your body have one nucleus, right? One command center. Muscle fibers are different. They can have thousands of these little command centers, and each one is responsible for managing its own little piece of the cell. So if you want your muscle to grow, you need more command centers. But where do they come from? Well, say hello to satellite cells. These are your muscle's own dedicated repair and reinforcement crew. They're basically stem cells that just hang out waiting for the call to action. And here's how that call gets answered. You go to the gym, you lift something heavy, that's the stimulus. That sends out a signal that activates these dormant satellite cells. They wake up, they start to multiply, and then they actually fuse with your muscle fiber. And here's the kicker. When they fuse, they donate their nucleus, their command center, to the muscle fiber. So more nuclei means the muscle fiber can produce more protein, support a bigger area, and ultimately generate more force. You're literally adding more management to the factory so it can get bigger and do more work. But what happens when we stop challenging our muscles? When we stop going to the gym? Well, our bodies are incredibly efficient. The system works in reverse. This is muscle atrophy. It's the cellular basis for that old saying, use it or lose it. If there's no demand, the body starts to downsize the factory to save energy. But it's not just that the muscle fiber gets a little smaller. Something much more interesting is happening. So what happens to all those precious command centers, those myonuclei we worked so hard to get? Well, they're systematically removed.
The process is called apoptosis, or programmed cell death. This isn't random damage, it's a controlled disassembly. The body is intelligently matching the muscle's size to its new, lower demand by getting rid of the command centers it no longer needs.
And the result is predictable. Fewer nuclei means the muscle fiber shrinks and its ability to produce force goes down. This is exactly why astronauts have to fight so hard against muscle loss in space and why strength declines when we're inactive for a long time.
So when you look at it all together, it's this incredibly dynamic system. On one side, you have overload from exercise, which activates satellite cells to add new nuclei, making the muscle bigger and stronger. On the other side, you have inactivity, which triggers the removal of those nuclei, making the muscle smaller and weaker. Our muscles are constantly adapting, adding or removing these command centers to perfectly match whatever we ask of them.
And this all leads to a really profound question. We have this built-in population of stem cells, this internal repair crew ready to go. So what could that mean for the future? For recovering from injuries? Maybe even for anti-aging? Or for pushing the limits of human performance? Understanding this process really does open up a whole new world of possibilities.